Okay, today we're going to finish Unit 2, Lesson 3, and we will go right into Unit 2, Lesson 3 activity. But first, let's do this final example. And this example right here says, consider the graph of two linear functions f and g that intersect at the point -4, -1. So this point right here is -4, -1. F has a positive average rate of change, and G has a negative average rate of change. And I want to know where f of x is less than g of x, and then, of course, we want to know why. I want to find this answer, and then I want to explain why. The first thing I'm going to notice is that I'm given that f has a positive average rate of change. That means f of x has got to be the blue line. So this is f of x, because it has a positive average rate of change, and g of x has a negative average rate of change. So this red line has to be g of x. I want to know where f of x is less than g of x, and I do understand that you may or may not have colored pencils in your notes. And so the question asks, where is f of x less than g of x? Kind of hard to see. We know f of x is this line with this positive, small positive slope. I want to know where that's less than g. Where that's less than g. Well, where is that less than g? And it's going to be somewhere on the x-axis, because when I solve these inequalities, I want to solve them with respect to some x. So if I take this point right here, let's just go this x value right there. Oh, golly gee, it doesn't look like f of x, which is this positive average rate of change, it doesn't look like right there that f of x is below g of x, does it? I mean, it doesn't. But is it? Yes, it is, because if I continue this g of x, and this is what's hard for a lot of students to think about, if I continue this g of x infinitely, because the domain of a linear function is all real, so this thing is just going to keep, that's kind of squiggly, keep going up and up and up, and eventually this yellow mark here will come up to the red, and the f of x is below g of x right there. So that point is, and I think it's easy to see right here, is f of x below g of x? Yes. But if I go over here at this point right here, is f of x below g of x? No, it is not. And it's hard to see. It's what you need to really realize is that this line here goes on forever, and that the domain of g of x is all real, so that eventually, if I did a vertical line, it's going to hit this red line. So the answer to our problem is f of x is less than g of x when x is less than -4. Why? Since the graph of f of x is below the graph of g of x there. Okay, that finishes, and there is a question like that on the assignment. There will be a question like this on the quiz. Okay, so now let's do Unit 2, Lesson 3 in class activity. What we're going to do is we're going to plot the data in the table and find a linear function that would best fit the data. There is a way to find this best fit with your graphing calculator, but we can also find the best fit line ourselves, and that's what we're going to demonstrate in this particular example. The first thing we're going to do is plot the points. Let's see. The y's go up to 17. So let's see how many ticks that we have. 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We do have 20 ticks, so it looks like we can do a 1-by-1 scale, and we will. So I'm going to plot the points 3, 4, 4, 6, and I would ask that you would do the same as well. 4, 6, 1, 2, 3, 4, 5, 5, 7, 6, 10, 6 goes all the way up to 10, 7 goes to 12, 10, 11, 12, 11, 12, 13, 14, 1, 2, 3, 4, 5, 2, 3, 4, 5, 1, 2, 3, 4. I think 5 went up to here. I think I had it off a little bit. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3. Okay, so that's 15. So 7 went up to 12, and I think I'm there. 8 goes all the way up to 15. 8 goes up to here. And then 9 goes up to 5, 6, 7, 8. 6, 7, 8, 9 goes all the way up to 17, which is here. So first of all, I need to recognize that one line doesn't go through all the points. But this is kind of easy. What we're going to do is find the line that best fits that data. So here's a line, and see, there's going to be multiple lines, but that line right there doesn't fit the data bad, does it? But what you really want to do is you want to take up one of the beginning points and one of the ending points to do this. Why students are uncomfortable with this is there are multiple correct answers. But true or false, there are incorrect answers. If I chose this line, let's do a yellow line. If I chose this line that went through those 2 points right there, would that be a good line? Would that line fit the data? Heavens to Betsy, no. But there are other lines that could fit the data nice, and we will choose. Let's choose, we want to start one of the beginning points. Heck, why don't we just use the first point and the last point just to make it easy. So we're going to use this point and this point. And I think if I took the line through those 2 points, that's not fun. If I took the line through those 2 points, I think that, like if I took this line through that line doesn't fit the data too bad. So let's just, so that we're all on this quote unquote same page, let's do those 2 points to come up with our line of best fit. Okay, so I want to name the linear function. And if I'm going to use these 2 points, let's just do the algebra now. I have this point 3, 4, and I have this point 9, 17. The first thing I need to do is find the slope of the line. And the slope of the line is going to be the change in y's, i.e. 17 minus 4, over the change in x's, which is 9 minus 3. 17 minus 4 is 13. 9 minus 3 is 6. So the slope of that line is going to be 13/6. I want a linear function, and the linear function is going to be this easy. Note, there are 2 different ways that you can write the linear function. Oh, I don't know why my green line is there. Oh, it's because I moved the screen. There's your 2 different ways to write your linear function. Guess which way I'm going to use? I'm going to use the point slope form because it requires less algebra. So I'm going to use the point slope form. I'm down here at the activity. I believe I'm here. And I am. Okay, let's see. 17 minus 4 is indeed 13. 9 minus 6 is indeed 9 minus 3 is indeed 6. So I want the linear function, and I'm going to use point slope form of the linear function. And that's simply going to be, I can choose whatever point I want. I can choose the second point or the first point. I'm going to choose the first point, and it's going to be 4, which is this y value, plus the slope times x minus 3. I do not have to put it in slope-intercept form. I do not. Okay, so, and I did indeed graph that line. That's the line that I came up with. The line that went through 3, 4, and that went up 13 over 6. So that was a pretty straightforward example here. I'm going to scroll down to number 2. What's going to be different for number 2 is the data is not nice data because of this 25.25, 16.4. So when we graph these points, all we're going to do is estimate their location. And if we look at the scale, first of all, let's see what the independent is and the dependent. A pediatrician wanted to find a linear model that relates a child's height to the circumference C of their head. The pediatrician selects 9 children and records the data in the following table. The independent variable, horizontal, will be the child's height. So this is our x, or this is our independent here, is the child's height. And the dependent variable will be the circumference of the child's head. So this is going to be our x, and then, if you will, this is going to be our y's. So what we're going to do here is we're going to plot this data, and we're just going to estimate the data. So here is a way to do this. If you look at the heights, they all range about 20. They range from 25 to 27. Here is the way that we can do this and make it a nice graph. What we're going to do down here on the independent scale, we're going to just do one of these. That means that there's going to be several data points or several inputs that we're not going to, that's going to change our scale. And we're going to start our scale at 25. And we're going to go, we go up to almost 28. So we're going to go up to 28 here. So 25, 26, 27. And now we can kind of get an estimation of where these x inputs, if you will, I hate to say x's, are going to be. And if we look at our outputs, we're going to do the same thing. It looks like our circumference will range from about 16 to not more than 18, so about 17. So again, what we're going to do is just make a little that says there's going to be a lot of missing points. And we're going to start up here at 16, I think will be good. Do we ever get to, well, we almost, we're going to go 17 and 18. Now, what I would like for you to do is just to estimate where those points are. Take a moment and plot those points while I pause the video. The thing you have to remember or note about a set of data, we can come up with a linear function that will model this. And if you should have observed that the input of 26.75 has 2 different outputs. So officially, this data, you couldn't call it linear data, but you can certainly come up with a linear model to represent this data and to estimate, because it's just a set of data. Now we need to create 2 points that's going to create a line that's going to best fit this data. I know what point we'll use. Why don't we use this line right here? Would that be a good line? Heavens to Betsy, no. That's not a good line, so let's get him out of there. And you get to choose. I bet these are hard for math teachers to grade because there's multiple correct answers. What about, you kind of want the same. I like that line. I like that line that's going to go through this point and this point right here. You see these 2 points? I like this point and this point because then I got some data below the line and I have some data above the line. So let's use those 2 points, shall we? You could choose your own 2 points if you want, but let's use those 2 points. So that point right there, that first point, if I'm not mistaken, is going to be 25.25, 16.4. So this is the one I'm using. 25.25, 16.4. This data looks like it's 26.75, 17.3. Those are the Can we agree with those 2 lines are okay? Those 2 points for the line are okay? So what do we need to do? We need to find the slope. The slope of that line is going to be the change in outputs. It's going to be 17.3 minus 16.4. And the change of inputs, 26.75 minus 25.25. I believe that is correct. Let me get this guy out of here a minute. He's bothering me. Delete that guy. Okay. So 17.3 minus 16.4. I think we could use that in our calculator. If not, isn't that 9? Isn't that 0.9? Is that 0.9? So that's going to be 0.9. And what is 26.75 minus 25.25? That's going to be actually, is that 1.5? 1.5? So let's take our calculator then and actually figure out what that slope is as a rational number. 0.9 divided by 1.9. So this slope is going to be 0.6. So that's the slope. And now I'm going to use either one of those points. Let's just use the first point. And so my linear model, call it whatever I want, let's call it f of x, is going to be 16.4 plus 0.6 times x minus 25.25. So that's my linear model. Look what I can do with that linear model. I can use that linear model to predict the circumference of a 26, the circumference the circumference of the head of a 26-inch tall child. To do this, if I want to predict the circumference of a child's head, a 26-inch tall child, all I do is this. I'm going to find f of 26, and I'm going to use that as an approximation. 16.4 plus 0.6 times 26 minus 25.25. And what does a 26-inch tall, what should the circumference of that child's head be? And if I do the arithmetic here, A 26-inch tall kid should have, the circumference of his head should be about 16.85 inches. Okie dokie.